Today's lecture is going to be on electric circuits and Ohm's Law. We're going to look first, chapter 34.1, at the flow of charge. When the ends of an electric conductor are at different electric potentials, charge flows from one end to the other. And that's kind of wordy and messy. Let's look at this battery here. That's what a battery is. That we have this positive side that's called a cathode, and we have a negative side that's called an anode. And it's going to literally push current from a high electric potential to a low electric potential. Then charge is going to flow, and charge flow is what we are going to call current. So when I have this very simple, one of the first circuits you've seen here set up, you're going to see that when we hook up wires, right, that are conductors, that the electrons are going to flow through that wire, right, through the conductor, and we're going to be able to generate electricity that's going to be able to make this light bulb come on. So we've got the battery that's really what's going to be pushing current, and this is the important stuff here. So we'll come into this picture a couple times. Charge flows when there's what's called a potential difference. That's what a battery does. A battery has a potential difference, high chemical potential to a low chemical potential difference, or a difference in voltage, and that's what a battery is, between the ends of a conductor. This is what pushes current in wires. It's the potential differential. So take a look here at this picture. Here's another way of looking at high pressure to low pressure. Water flows from high pressure to low pressure. The flow will cease when the difference in pressure ceases. So when this water stabilizes and all the pressures are equal, it'll be nice and stable and balanced. Water continues to flow in this scenario because there's a difference in pressure that's maintained by the pump. So the pump is constantly pulling water from here and pushing water to here. So a pump is actually driving it in this case. So 34.2 talks about electric current. Electric current is the flow of electric charge. Right, we studied electrostatics, which was forces generated by unmoving charges. Now we're going to start putting those charges into motion, and that's what we call electric current. In solid conductors, right, wires, something metallic, electrons carry charge through the circuit because they are free to move throughout the atomic network. Protons are bound to the atoms within the nuclei, but atoms are not fixed, so they can move when there's a push from the electric potential difference. It's essentially looking at the battery voltage, actually pushing on them. So the battery is what's going to be pushing the current. So battery here is going to be creating this potential differential. It's going to push current. And current is what we're going to look at. These are just going to be moving electrons here. So current is going to be measured in amperes, which we'll call amps, which will be the symbol letter A. So if I look at this picture here, we're looking at what's called the flow of charge. It's going to be moving from left to right. And if this would be a kind of a cross-section of the wire. When the rate of flow of charge past any, in this case, cross-section is 1 coulomb, the current is 1 amp. And we'll start putting numbers to this very, very soon. But it goes back to this. Your battery is going to provide voltage, a chemical potential difference. It's going to push current through the wires. And when that wire interacts with, in this case, a bulb filament, it's going to heat it up. And that's going to generate light. Moving on. So now we look at voltage sources. Something must provide the potential difference in a circuit. Batteries and generators provide a voltage source. There's often some confusion between charge flowing through a circuit and voltage being impressed across the circuit. Water, if you look at the picture below, only flows if there's a difference in gravity, where water flows downhill towards the lower end, right, from the higher end. So look here, if I have water in this tube here, it's just going to rest there. But if I lift one end up, it's going to flow from the higher end to the lower side. It's simply the height difference is what causes the water to flow. So the change in height causes water to flow in the pipe. Well, that's the same concept with current. In this case with voltage. Voltage is going to be like lifting it up. So no voltage, so no charge flows. The bulb doesn't come on. There's no voltage. There's nothing pushing current here. But as soon as I hook it up to a 1.5 volt or 1.5 volt battery, you have the chemical potential. It's like lifting up this tube of water, and the water is going to move here. By hooking this up to a voltage potential, you're going to get current to flow through here. So current flows in a circuit because a battery creates a voltage difference. So similarly, charges flow, which is what current is, through a circuit because voltage is applied across the circuit. Voltage causes current. Electric currents provide energy for light, among many other things. So here's a battery that we'll be working with 1.5 volt batteries, and we'll be setting them up into very, very simple, what we'll call series circuits very soon. So the third part of this, 34.4, talks about electric resistance. The amount of charge that flows depends on the voltage provided by the source. For example, two batteries provide more voltage and thus more current. The current also depends on the resistance of the flow within the circuit. So if you have a bunch of resistors, you're going to decrease the amount of flow of current. The resistance of a wire, or resistor, depends on the conductivity of the material being used in the wire, the thickness of the wire, and its length. So let's look at these two jugs of water. I feel like it's important for you to understand what resistance is. If this both have water, and this container here has a really large opening, and this one here has a really small opening, this one here is going to provide more resistance. It's going to only allow that water to flow out at a much slower rate than if you have a larger opening. Well, that's kind of what resistance is. Low resistance means this is going to come pouring out much faster. Whereas here, you've got a lot more resistance. It's going to come out slower. So thick wires have less resistance than thin wires. Long wires have more resistance than short wires. Electrical resistance is measured in ohms. We're going to get used to this word, ohms. So if you're meditating, make sure you're meditating by going ohms. Okay, I move on. And is represented by the symbol omega, and that's what this symbol is here. So for this case here, for a given pressure, more water passes through a large pipe, in this case, than a small one. So we're really talking about more electric current passes through a large diameter wire than a small diameter one. So in this case here, more water coming out, more current. Less water passing out, less current. So 34.5 is called Ohm's Law. It focuses on Ohm's Law. And this is really the holy grail of electric circuits. We're looking at voltage equals current times resistance. So the relationship among voltage, current, and resistance is defined by or called Ohm's Law. Ohm's Law states that current in a circuit is directly proportional to the voltage across the circuit and inversely proportional to the resistance of the circuit. So voltage equals current times resistance. Now buckle up, because Ohm's Law is going to be something we are going to be using for the next several weeks, actually months. Ohm's Law will be used to quantify how much of something we are trying to measure. We can see that voltage, current, and resistance are all related, and specifically by how much. So Ohm's Law looks like this. Voltage equals current times resistance. Voltage is identified by the symbol V, is measured in volts. Current, letter I, don't ask me why, is measured in amps, or sometimes I'll refer to as amperes, but generally I'll call amps. And resistance, R, is measured in ohms, and generally we'll use the symbol omega. So if you looked inside a, let's just say any type of a circuit board, the stripes on these resistors are color-coded, indicates the resistance within them. That you have all kinds of different resistors within different circuits. We'll explore this a little further. So 34.6 talks about Ohm's Law and electric shock. What causes electric shock in the human body? Current or voltage? Well, the damaging effects of electric shock are the result of current passing through the body. The resistance of your body depends on the condition and ranges from about 100 ohms if you're soaked with salt water to about 50,000 ohms if your skin is very dry. The less resistance of the body, the greater the current passing through. So since water is a good conductor of electric current, water and electronics can do damage and even kill a person. This is called electrocution. This is not good. So if I look here at various amounts of current that are going to do, let's just say we can feel. We'll start with that. Electric currents on the body. So current measured in amperes or amps. 0.001 amps can be felt, right? That's like a little zap. That's like what the Van de Graaff gave us. Tiny current, but you could feel it. 0.005, that's 5,000th of an amp. Would be painful. You'd be like, okay, boom, ouch, boom, shakalaka. You might say 1/100th of an amp would actually lead to involuntary muscle contractions, like spasms. You'd be like freaking out. When we talk about 0.015, that would be 1500ths, we would talk about loss of muscle control. You could technically soil yourself. They would just lose all muscle control. Not good. Also not good. Electrocution, soiling self, not good. And we've got 700ths of an amp. If it's traveled through the heart, this would be serious disruption of your heart pumping. It would probably be fatal if it lasted for more than 1 second. That's not good, right? We don't want fatalities here. So moving on into electric shock. Electric shock is, if we would look at a bird that's perched on a wire, on a high voltage wire, would have no effect of the electric current because there's no difference in the potential in any part of the body. So current doesn't flow. But if they were to touch something else, something bad would happen. So in theory, and I don't recommend it, but if you could hang, that's supposed to be hang from a very powerful power line, right? Like this bird, you would be fine, you would be safe. But only if you touch something would you be in danger, because current would travel through you. It would go from a high to a low potential difference. But hanging from the wire would lead to no potential differential, so no current would flow through you. You got to check out what happens to the squirrel when it touches another line. Well, let's just say a little Zappageweia. So 34.6 talks about electric shock a little further. We look in here at electrical appliances that are connected to ground wires, and that's what this third prong is. At third wires, the ground wires are actually, they're helpful for devices in homes. Mild shocks occur when the surface of an appliance are at an electric potential different from that of the surface of the nearby device. If you touch a surface of different potentials, you could provide a pathway for the current. So you'll see here that this squirrel, once again, same video as the one before, it receives a potential difference of about 400 volts, leads to a current of about 15 amps. That is a tremendous amount of current. Not good for the squirrel. Moving on into 34.7, we're going to talk direct current, DC current, that's using batteries, and alternating current. That's like plugging something into the wall. Electric current can be DC or AC, so direct current or alternating current. DC means direct current, which refers to the current flowing in one direction, right? Boom. A battery produces direct current, or DC current. Electrons move in the same direction from the repelling negative terminal towards the positive terminal. But alternating current is electric current that repeatedly reverses direction. It's literally moving back and forth. Electrons first move in one direction and then in the opposite direction, alternating back and forth in a relatively fixed position. Generators, such as plugs that we use regularly, use alternating current. Nearly all commercial AC alternating current circuits involve about 60 hertz of current. In this case, where it cycles back and forth 60 times per second. And we can actually convert alternating current to direct current. The current in your home is alternating current. That's what you plug into. The current in a battery-operated device, is like a cell phone or laptop, is DC. So when with an AC or DC converter, you can actually operate a battery-run device on alternating current instead of batteries. The converter uses what's called a diode, a tiny electronic device that acts as a one-way valve to allow electrons to flow only in one direction. So 34.9, the speed of electrons in a circuit. When you flip the light switch on your wall, the circuit is completed and the light appears to glow immediately. Energy is transported through the connecting wires at nearly the speed of light. The electrons that make up the current, however, do not move at this high speed. When the electrons are moved in an electric field, flipping the switch pushes the electrons in a specific direction. Right? We're moving this in a particular field. And here at 34.10, the source of the electrons in a circuit, the source of the electrons in a circuit is the conducting circuit material itself. It's the wire. The wire provides the electrons. Just as our clothes and we provided the electrons in electrostatics, the electrons are already in the wire. Some people think that outlets in the walls of their homes are the source, but that's not true. The outlet provides the potential difference. The outlets in your homes are alternating current, so electrons do not travel much distance through a wire. Instead, they vibrate back and forth in a relatively fixed position. So when you plug something into an outlet, energy flows from the outlet into the lamp, not electrons. Electrons are already there. The electrical energy appears as heat in the filament of the light bulb. When heated, bulbs light up. Power utility companies do not sell electrons, they sell energy. You supply the electrons. And we'll finish up here with electric power. Electric power is the rate at which electrical energy is converted into another form, such as mechanical energy, heat, or light. Electric power is equal to the product of current and voltage, so P equals IV, where power equals current times voltage. You pay for what's called kilowatt hours. It's between 1 and 10 cents per kilowatt hour, depending on where you live. A kilowatt is 1,000 watts. A kilowatt hour represents the amount of energy consumed in 1 hour at the rate of 1 kilowatt. Different household appliances demand different amounts of power, thus have different operating costs. When we look at electric power, we're going to be using this concept of that we're going to measure in watts, but we're really talking about current times voltage, and that's what this equation is. P equals IV. It's measured in watts here. Utility companies charge customers for the number of kilowatt hours used each month. 1 kilowatt hour is equal to 3.6 million joules of energy. So electric power here, and I'm winding down with time here. So electric appliances are powered by electricity measured in watts. Electric power is the rate at which electrical energy is used. So in this case, the watt is abbreviation for a measurement of energy. You need to make sure that you are able to solve this set of slides here and here,